Hello there, welcome to the second part 2 video about transition metal chemistry. I know this is the last common topic that is not assessed, but as I mentioned before, there may be some context is related to transition metal which will help you, but it helps to help you in the exam question when you understand the context. So let's carry on with going through the topic main concepts here. Now the consolidation practice here for the suggested answers for the consolidation practice will be uploaded together with this video. So you can also, if you decided to try your hand at doing some of the questions here, you can actually also take a look at them and take a look at the answers and okay, for your own self monitoring and self learning. Now, the last time round we ended off actually at the atomic and the physical properties of transition metals actually, and we were actually going into the start of the transition metal chemical properties. Now, I thought it would be just good to recap some of these points because it was done quite hastily in class. Now, basically, transition metal can actually form complexes. Now, what is this thing called complex, which is like sounds so complicated? Okay, now basically a complex ion is just simply one that contains the transition metal cation usually. It can also be the atom and surrounded by atoms or molecules known as ligands. And these ligands are actually bonded through dative bonding to the metal center. Now, why is it able to do so? Because transition metal actually have high charge density, because usually they will have a charge, for example, or at least they will have an oxidation state at least of something like +5, +6, okay, and they can actually attract the ligands, okay, to with a lone pair of electrons. So what is known as a ligand or ligand? Ligand if you are staying in America, ligand if you are staying in the UK, okay, or Singapore, for example. A ligand is actually an ion or a molecule with a lone pair of electrons that can do dative bonding with my transition metal, okay, ion or atom here in this case. Now, why is transition elements able to do so? Not only because of high density, because in the first place there's actually vacant d orbitals that are energetically accessible to accept the electrons from the ligands to form dative bonding. Now, unlike your ionic compounds here, ionic compounds, the coordination number is the numbers of nearest neighbors in the lattice crystal structure. Whereas transition metal, the coordination number is the number of dative bonds actually surrounding the transition metal atom or ion here. Now, there's a reason actually because later actually influences the shape. But before that, maybe I should also mention about something about the ligands here. Now, the ligands can form one or a number of actually dative bonds with the transition metals, and that is what is known as the datateness of the ligand here. Now, of course, a ligand can be a neutral molecule or an ion. Usually, cannot be a cation because they will repel the transition metal cation. Okay, now, but as I mentioned just now, the number of dative bonds actually that a ligand can actually form with transition metal can vary. Now, if it only forms one dative bond, for example, here in terms of water, ammonia, okay, or the SCN, SCN actually can use the sulfur or nitrogen to form a dative bond here. Okay, basically this only can form one dative bond per molecule or per ligand here, so this is known as a monodentate. A bidentate is something like this here, though, diethylamine, or you can actually have two nitrogens here with a low pair of electrons that can form dative bonding with the transition metal atom or ion. Something like ETTA4 plus, which is actually the structure here, you don't actually know the chemical name strictly speaking. You just need to know it's ETTA. Can actually form 6 dative bonds per one ligand molecule here. Now, so these are some of the common names. Now, the complexes can be neutral and can ionic or anionic, whether you follow the charges, the rules of the redox. Okay, the redoxing charge, you see the charge of the ligands and the metal can ion. Okay, or center metals, transition metal center here. So, for example, here, let me just very quickly go through iron hydroxide here. This is because of the hydroxide ion here, because it's -1. This will tell you that iron is actually +3 oxidation state here, because water here is actually neutral. Now, as a very quick check that I have done this before, I'm just therefore show you the answer for the quick check that I've done. Okay, in part 1 here, very quickly. Now, as I also mentioned in part 1, that means the number of dative bonds surrounding or the coordination number of a transition metal ion or complex, therefore tells you the shape. Now, usually these will only fall into 3 categories, 2, 4, or 6 here in the syllabus. Of course, you can have 5, dative bonds, and then if you find dative bonds and you use the VSEPR theory, then you know that therefore it should be trigonal bipyramidal, but these are not so usual. Usually it'll be 2, 4, and 6 in the syllabus. If you have 2 dative bonds, then you'll adopt a linear shape, because for example here, this is silver, is the transition metal ion center. Okay, then you have the ammonia arranged in a linear fashion around this complex here. So this is your diamine silver, which is actually your tolerance reagent. Okay, let me take a drink here. Okay, next 2. Now, if it's 4, you can actually have 2 possible shades. And this depends on the transition metal center actually. You can have a tetrahedral shape, which is more usual. But you can also have a square planar shape. And this square planar shape is one of the most famous compounds, is like your cisplatin, which is actually one of the first few anti-cancer drugs that is actually found, was ever found here, which was actually high toxicity, but at least it was still able to prevent these cancer cells from actually multiplying. Then, of course, when you have 6, dative bonds here, you'll be adopting the usual octahedral shape here in this case, and you can see some of these compounds here, in terms of the, how to draw and depict them. All right. So anyway, let's move on. Now, one thing about the complexes there, because they say they're very complex, right? Is that fact that therefore, you can actually exchange the ligands here, because they can actually depend on what you have. You can actually sub in one of the ligands and exchange it out for another one. Now, this depends on, of course, how the ease of the ligand exchange. And basically, the idea here is that a stronger ligand, will replace a weaker ligand from the cation complex here. A little bit like how a stronger oxidizing agent will actually stronger oxidizing agent like a metal here, the more reactive metal would displace the less reactive metal. A little bit like that here, but here we're talking about the ligands here. So if let's say, for example, here in your, here I have actually 4 ligands around my metal center here. Now I can sub on one of the ligands here with Y. So Y is obviously a stronger ligand than my, L. But not only that, therefore, this also means that the ML5, sorry, it sounds only 6 here, ligands here, but basically your ML5, ML5, sounds like MI5, right? Or MI6. ML5, why here this complex here is actually more stable, because you form a stronger ligand, because the dative bond, for example, can be stronger, so that means there's more energy being released during the formation of the dative bond between Y and M. So this compound here, ML5Y, will actually have lower energy, which is why it's more stable here. You can see that, for example, here, these are actually usually classical. Now, the examples that you're going to see now are the classic, book work, what you need to know, at least for transition metal. But now, of course, because it's not assessed here, it may actually be tested either in terms of application, but you don't have to do a recall. But for example, here in this case here, when you actually add copper, when you add actually con HCl, sorry, to your copper ions here. Now, copper ions here, aqueous ions are actually blue. Now, by the way, when we write down aqueous here, just like in your periodic table, we actually mean that therefore usually there are 6 water molecules surrounding my copper 2+ ion, which means that this is an octahedral complex here. So as you can see that therefore the question tells you that HCl, as you add con HCl, you actually turn green. Now why does it turn green is because in the first place here, and the question tells on to tell you, and something that actually you need to previously remember but now you don't, is that copper chloride, this copper chloride with 4 chlorine, in terms of complex here, will actually be yellow. Now, obviously, the green color is a mixture of the blue and the yellow. So how do you actually account for this? Now, obviously, then for your Cl minus ions, it's acting as a ligand to replace the water ligands here. So it's actually stronger ligands than your water here. So it will actually form this complex, which is yellow. And as you form the presence of both the blue and the yellow, gives you the resultant green color here. Now, another example you need to know last time is basically how carbon monoxide is actually poisonous actually to us humans here is because of this idea again of ligand transfer or ligand strength here. Now normally we have hemoglobin which actually can bind to 4 molecules of water here. This is have your bio people will know that 4 alpha 4 beta heme. And there's the heme ligands actually bound to an iron center here in this case. Now the oxygen therefore can actually swap out the water. Now what oxygen is not very much stronger than the water here, so this actually exchange is actually reversible, so that you can actually free up the oxygen when it comes to the cells. The oxygen can be liberated from the hemoglobin so that it can actually diffuse through the cell and where it's needed. And for example, and whereas when you actually have the lungs where you have the water ligand, the water acting as ligand, oxygen can replace the water so that you can get an oxygenated hemoglobin so that it can be transported to the relevant places in the tissues in the cells here. Now, So this actually oxygen here and your water is actually because of the fact that the ligand strength is actually quite similar. This reaction is reversible. So you get oxyhemoglobin and the deoxyhemoglobin being formed and exchanged regularly at the lungs and the cells here. Now, there are certain things that are toxic by your cyanide and your carbon monoxide here. Now, why are they toxic? It's because mainly they bind to the iron by a stronger, because they are much stronger ligands, they actually form stronger dative bonds with your iron center. Okay, and so they replace the water, but they refuse to let go of the iron. So the hemoglobin basically now is rendered useless, and the hemoglobin will not be able to form oxyhemoglobin, and of course, eventually you will die of oxygen, die of the lack of oxygen here in this case. Now, take note, however, there's something that you might want to take note in terms of the name or the term being used. Ligand strength. So here we can say that the cyanide and the carbon monoxide are stronger ligands, but that doesn't mean that they are strong field ligands. When you see the word field, it actually means something else here. You will shortly see this actually, especially under terms of color, under the nature of the ligands here. Okay, so something to take note here at the moment of time. Okay, but let me continue on and let's talk about how the properties of transition metals and their complexes. Obviously, the transition metal can actually still exchange or for that matter to gain or lose electrons, and so even in the complex form, they can actually have variable oxidation states. Why? Because the 3D and 4s orbitals are basically very close in energy, so they can lose a variable number of electrons to form various complexes or various ions of the similar stability here. So you can see here these are the most common oxidation states. These are all the possible oxidation states from scandium to zinc. But remember, scandium and zinc are actually not transition metals, strictly speaking. Okay, so we should be talking about titanium to copper. Now, these are the possible oxidation state, and you can see that therefore, they're also the hostile oxidation state. They're common. Okay, they are both in red here. But take note, there's something else there to take note of this list here, because if you want to contrast this later as the possible oxidation number here, for example, of the titanium all the way to copper, right? Because if that's the so, then the iron actually onwards should actually keep increasing. You should have +8 oxidation state for iron, cobalt, and then nickel and even copper respectively. But you notice that their trend goes down, after manganese. Shortly about. Now, as I said, you should compare this with your main group elements, especially S block, because that's what you're supposed to do in the syllabus actually. Because S block elements, of course, have a fixed oxidation state, whereas the group 1 will have +1 and the group 2 have +2 oxidation states here usually. Now, because once the sp orbitals are improved, the p orbitals that are removed next here usually will come from the inner quantum shell that requires more energy, and of course, this will be unfavorable and requires large amounts of energy here. Now, take note here. Now, there's also a common misconception that the possible oxidation state of the transition metal is basically the number of D as well as the 4s electrons. That's not true, because the maximum oxidation state that can exhibit is basically the number of 4s electrons plus the number of unpaired 3D. Okay, take note here. So now, by the way, the most stable oxidation state you actually may have to explain, which actually I think is not difficult to explain, because you can just apply things like the idea of atomic structure here. So for example here, if you notice the E0 cell values here, the negative E0 values here, you can see that therefore from titanium to chromium means that therefore they are good reducing agent because they can get oxidized easily. Whereas the positive E0 values means that the M3 plus is a good oxidizing agent because the M3 plus ions are easily reduced here. And chromium 3 plus and manganese 2 plus are the oxidation state that are common here. Now you can see that why is basically now the E0 values of the +3 oxidation and +2 oxidation state for manganese is more positive, whereas the iron is more negative. Now this is actually really because of the fact that you have your half-filled electronic configuration, as well as the fact that your 3D orbitals, for example, the removal of the electron from the iron 3 plus here, 2 plus, sorry, removes it to form the iron 3 plus. Therefore, you actually remove an electron from the W filled 3D orbital, which I mentioned before, will have inter-electron repulsion. Whereas if we talk about Mn2 plus, it's more difficult to actually remove the electron because you are removing an electron that disrupts the stability that's rendered by a half-filled 3D5 electronic subshell. That's basically it. Now, basically, just as to do a quick check here, if you would like to pause the video, you might want to do the quick check, actually involving 4 questions here in this case. I hope you know what to do here. For the quick check here, this is actually something doable. The titanium should have a 3D2 4s2, electronic configuration as the outermost. Titanium 2 plus therefore removes of the 4s electrons, so you should have your 3d1, and I'm writing them in the noble gas core here, which are allowed because the question did not ask for the full electron configuration, unlike question number 1. Now, why does titanium possess only a maximum oxidation of +1 all the way to +4? Because the number of 4s electrons, okay, plus the 3d unpaired SH4 means that, okay, the maximum oxidation state is +4. Now, which of the titanium compounds therefore is not likely to exist? Therefore, you can see that therefore the next question here, the A should be the answer because you should have an oxidation state of +6. The maximum oxidation state that actually you have is actually only +4 here in this case. So that talks about the transition metal, okay, complexes in terms of their ability to have various oxidation state, and therefore, and also their ability to actually, for example, act as oxidizing or reducing agents respectively. Okay. Now, the next is basically on what is basically very, very commonly tested last time. Okay, but it's not been tested for 2 years already, I guess. Okay, it's basically the color of transition metal complexes. Now, I hope you remember, at least from the O levels, maybe not from me, but maybe from the O levels, that the transition metal often actually appears as colored compounds. Now, this is mainly because of what, okay, now the theory that we use to explain this is known as the crystal field theory. Now, the crystal field theory requires you to know actually quite well your atomic structure involving the d orbitals of your transition metal. Now, normally remember that the d orbitals, okay, in a free, okay, atom or ion, okay, will be all degenerate. Take note that word degenerate means that they are all having the same amount of energy, same energy level, huh? So that's why they are, if you put a vertical energy here, axis here, okay, they are all found on the same line here. Now, when the ligands, however, approach them in a, okay, approach to form a complex, either the, okay, now in the octahedral complex here, for example, the d orbitals will have suffer repulsion here, because if you think about it, let me just quickly show you. Let's say, for example, I'm talking about the d z square. It's a d z square orbital. Okay, a bit lopsided. Okay, the word should not be so big. But let's say, for example, the dz square, okay, which obviously will lie on the z-axis here. Now, if your complex is coming from an octahedral complex, octahedral manner, it means, let's say, for example, now I have your ligands here coming in the octahedral. Okay, so this will be your z, this will be x here, and then this is your y. So they will be coming from these regions here. You can see that therefore your incoming ligand, the lone pair of the from the dative bonding, would have, okay, come and approach the d orbitals, okay, the electrons here in your transition metal complex head on here. Now, of course, that will form a dative bond in the sigma bonding, but not only that, as they approach here, the the dz square orbital will actually, because there's actually electrons and there's actually electrons in the incoming dative bonding, okay, they will actually have repulsion here. So the dz square, okay, orbital will actually have higher energy, and comparatively to the, for example, if I were to draw for you the dx, or this I'm drawing actually the dy, okay, this is the dy dzy orbital here. Maybe let me draw it properly, just a minute. I should draw the dx here. This is the dxz orbital, because the dx orbital lies in between the orbital, in between the Cartesian axis. So any approach of electrons from the along the z-axis here or the x-axis here will not suffer that much repulsion compared to an orbital like dz square, which is actually lying on the Cartesian axis itself. Now, if you notice, therefore, there's only two orbitals that lie on the axis of the Cartesian axis, which is the dz square and the dx square minus y square. So these two orbitals suffer greater repulsion, and so this is why they would actually have greater energy as the ligands approach here, whereas the other three will have lower energy here in this case. So this results in an energy gap delta E. Okay, now, but if it's a tetrahedral complex, by the way, it's the other way around, because if you approach the ligands, okay, use the dative which the dative bonds actually are formed along the tetrahedral axis here, okay, basically they will tend to therefore impact the, or basically have a more repulsion with the orbitals that are lying in between the axis here, because the tetrahedral shape is actually where the orbitals are, the dative bonding electrons are actually coming from more like in between the axis, Cartesian axis direction here. So that's why you see instead the three orbitals that's on top are the associated ones at the xy, dxz, and the dyz. Okay, orbitals will be the one with higher energy. Okay, so basically, if there's an energy gap, an electron can actually be hopping, let's say for example, found in the lower energy gap here, the lower energy group here, can actually have, absorb energy from light, okay, and therefore goes up into the partially filled or empty d orbital, okay, in the top, okay, higher energy group here. Now, this doesn't actually cause color here, but instead, okay, when they, okay, so this is not the color that actually is as a bit, but because of this absorption here, now this absorption will therefore correspond to a certain wavelength of light, but the remaining colors that are actually not absorbed therefore appears as the color comes observed. The D transition here is talking about D transition. The difference between the two energy gaps here. So this is where you need to know your color wheel, which is actually easily constructed. You actually just have draw a circle like pizza, and then you actually divide your pizza into 6 pieces here, like what I'm doing now. Just remember that it's like if you actually watch the X-Men with the X-Men logo, okay, as I always say, you draw a circle, X-Men, mutant, then you just cross it out one more. Okay, then you just actually now you can start anywhere. You can start any clockwise or clockwise, doesn't matter. Red, orange, yellow, green, blue, and then indigo. So let's say you absorb the red color spectrum from during the DT transition, okay, basically, okay, this term with the transition, you actually, the complex will appear green. If you absorb blue, you appear orange. Okay, so the opposite end of the color, which is the complementary color, will be seen instead. Okay, so this is what it governs the color here in this case. So sometimes you can absorb two different colors. For example, you can absorb away your indigo and orange, and then they will get you blue and yellow, and then it will still give you green as well. But that kind of examples are far fewer, okay, at least in the A-level syllabus here. Now the color is actually dependent on of course, the energy gap here, delta E, which depends on the wavelength of light. So if you have, if you absorb a, if you have a big delta E value here, you absorb a shorter wavelength, which is actually your, okay, it will go towards the blue. If you absorb a small delta E here, they will absorb a long wavelength, which is actually your red color here. So that will see the splitting energy here, the amount make a difference in terms of your, okay, color. Of course, it also depends on the transition metal oxidation state, because the number of electrons therefore affect the repulsion, okay, on delta E. Okay, so therefore, and of course, because in order for your DT transition to take place, you must have actually empty d orbitals, okay, or partially filled. Okay, so there's actually frequency on the upper energy group for you to do the DT transition. So basically, if you have, okay, complexes with your 3D 0 or 3D 10 electronic configuration, this will be white solids, because there's no electrons in 3D 3. If you don't have 3D electrons, there's not possible to have DT transition. If you have a fully filled D subshell, okay, that means there's also DT transition, because there's no ability for the d orbitals from a lower group to actually go up to the high energy group, because there's a lack of space. So this will tell you basically how come copper 1, scandium, and zinc compounds are actually not colored. Okay, because of that here in this case. So that covers the color here. Now another thing about the color house, because now you can see just now when we talk about the octahedral versus the tetrahedral, the splitting pattern is different. You get 3 orbitals on the top, the higher energy level gap, compared to 2 orbitals in the higher group of your energy here in octahedral. So that will affect the shape of the shape or the coordination number of the transition metal complex, therefore affects its color. Now the nature of ligands, and this is where I mentioned just now the ligand field strength. Now the ligand field strength roughly has this, okay, here. Now you do not need to know actually the exact sequencing, okay, but okay, roughly here you just need to know that a weak field strength ligand results in a small delta E, and of course that means that you absorb a long wavelength of light. If you have a strong field ligand, it causes the delta E, the energy gap, to be bigger, and so you absorb a short, okay, wavelength of light here. And so this is how, for example, previously if you were doing this question, for example, how come iron, okay, in terms of water, iron 2 plus is actually, okay, green, whereas if it's a cyanide ligand, actually it's a yellow, because the cyanide ligand is actually a strong field ligand, resulting in a large, okay, energy gap, okay, between the lower energy group and the high energy group. So it results in the shorter wavelength being absorbed here, which means that therefore the longer wavelengths, which is basically corresponding to yellow, okay, will be absorbed here or emitted, sorry. Whereas the weak field ligand like water actually causes the delta E value to be delta E energy gap to be smaller, which then means you absorb longer wavelength of light, which then leads it to actually emit the colors that's actually of a shorter wavelength, which is in this case actually to be green. Okay, so long time ago, actually, or at least not so long ago, 2 years ago, if you have this kind of question, you actually need to remember which wavelength, or at least which spectrum or wavelength, okay, correspond to your, okay, which color light here. So for example, if you see something that is green, or at least something that is nearer to the blue region, that means the longer wavelength are actually, so let me just quickly again, let me summarize this. Okay, as I move it up again. Okay, if you see something that is actually red, a strong field ligand actually will absorb your shorter wavelength, so therefore the longer wavelength will be seen. So this will be in the red or the orange region. Whereas if you have a small delta E, you absorb the long wavelengths, that means that for your shorter wavelength here, which means that it's higher energy level, okay, this will be your blue and your violet colors actually being seen here in this case. Okay. Now, therefore, the last, let me just reiterate that the field strength is not the same as a strong, or that means that whether on the ability of a ligand to be strong or weak to kick out another ligand here, even though there's kind of a correlation usually. Okay, for example, here, if you form a stronger bond with your, usually when you form a stronger bond with your metal complex here, okay, or metal ion here, you usually therefore have the electrons therefore, okay, coming in closer, for example, and cause a larger energy gap, okay, difference, but that may not be so here talks about basically your catalytic activity here, which is actually going to be summing up here. And so, by the way, sorry, that actually, okay. Now the last part is actually on the catalysis here. Okay, the catalytic activity, you need to know how transition metal actually function as a metal, how can they function as catalyst. And remember, this was done in kinetics, which I mentioned will be covered in transition metal. But because this is no longer in the assessed in the syllabus, you do not need to know this as a factual fact. But perhaps again, as I said, you may need to know this as an application. So basically, heterogeneous catalyst, remember, is when the transition metal, okay, or the catalyst is in a different state compared to your reactants here. Now, transition metals are good, okay, heterogeneous catalyst, okay, it's not heterogeneous catalyst because there's ability of the 3D and 4s electrons to form temporary bonds with the reactants. So this, for example, the best example you can give is your Haber process, or basically your heterogenation of alkenes. Now, previously you need to know this as a factual recall, but just to be good and remember that anyway, iron, okay, in the Haber process is used as a heterogeneous catalyst. Now, what happens here is actually you need to know the actually the mechanism, actually the absorption. Now, here take note that it's absorption. Absorption means that therefore the molecules are bound onto the surface rather than absorb, which is like a sponge where the molecules are found into the okay compound or something like that. Okay, so this absorption here, now this absorption occurs because you can form temporary bonds between your reactant molecules by using with the transition metal surface using your 3D and 4s electrons. So they are on the okay active sites here, okay, on the transition metal surface here. So there are two pictures here, so depending on which one you can see, but of course you need to draw something like that over here. The one here on the left is of course okay for your okay hydrogenation process. Now when this absorption occurs, you basically okay improve the rate because you weaken the bonds, which is the activation part. You weaken the bonds between your reactant molecules, and therefore you also bring them nearer to each other. So it increases the concentration, surface concentration of the reactants, so that they will be nearer to each other to react, and therefore finally they are brought closer, and then when they react, then dissolution must occur. So if the dissolution doesn't occur, that means there will be no catalytic effect as well. In fact, the catalytic surface will be poisoned, okay, because you will not be able to okay absorb any more subsequent reactant molecules, and also the reactant molecules after they reacted they also cannot flow away, so you basically have not, they're basically stuck here in this case here. So dissolution process is actually also required. Okay, now homogeneous catalyst, however, is operates by a different mechanism or different pathway. Basically, this, remember, homogeneous catalysts are the ones where their catalyst is actually in the same state as your okay reactants here. Now, the reason why therefore transition metal can do homogeneous catalysts in this case is because they can exist in various oxidation state, okay, and basically the the various oxygen they have similar or relatively similar so-called stability, so they can transit between the various oxidation state easily. Now, as I said, also you need to know one example previously, and I go quote you and to know that this example here is actually quite useful because it's a reaction with your peroxo disulfate, okay, with your iron minus here, the iodide, using iron 2 and iron 3, okay, as a homogeneous catalyst here. Now, why is this reaction actually in first place very slow? It's very, even though the reaction is feasible. Now here you'll notice that your S2O82 minus is actually being reduced, the I minus iodide is being oxidized. So if you actually calculate, cell is actually feasible. But this reaction has a very high activation energy, which is why it makes it slow. Because if you look at the starting reactant molecules, both of them are negatively charged. So there will be repulsion and they will not likely come together to do collisions, effective collisions to result in the reaction here in this case. So the speed of this reaction is actually quite slow. Now you can actually make this reaction faster by using iron 2 and iron 3. Either way, either one of them will do, because iron 2 and iron 3 in fact is will transit between the two oxidation state of +2 and +3 in this when they're doing the catalytic activity. If iron 3, you will react first. Now iron 3 is going to get reduced to iron 2, so therefore it's going to go to your iron minus first, because that's the one where you get oxidized. So iron 3 is going to get reduced, right? So you notice here iron 3 can get reduced with your iodide, and this E0 cell is actually positive. Okay, so this reaction is feasible, and of course this is a favorable interaction, because you have a cation reacting with an anion here. Now after it becomes iron 2, the iron 2 can therefore go to your peroxo disulfate and react with the peroxo disulfate and oxidize your peroxo disulfate here in this case, and the iron 2 reduce the peroxo disulfate, sorry, and therefore the iron 2 gets oxidized back to iron 3, and therefore now my catalyst is regenerated and can do another round of catalysis, and in the process therefore my the peroxo disulfate actually now also reacts with a cation species, and therefore this is a much faster reaction, because now your oppositely charged ions are involved and they attract each other, and this speeds up the reaction and by lowering the activation energy. So so here actually the catalyst works because the catalyst is a different charge, and also but you must also realize that you also need to check that therefore the E0 cell value of this reaction is feasible, as the catalyst transit between the two forms, and they were able to catalyze reaction by with your iodide and your peroxo disulfate here in this case. Now one common question to do is really to realize that last time is where you can use your E0 value, because there are actually other redox couples that can actually react and catalyze your this reaction here. You might want to search for on your data booklet, and your answer should also clearly show how you can use it using E0 cell calculation that is possible here in this case. I will therefore pause here, and you should therefore spend about maybe 8 minutes to try to solve the more than one answer here. In this quick check here question. That sums up basically for the whole of your transitional metal chemistry here in this case. Now if you've done the quick check here, basically the possible ions here are cobalt 2+ and cobalt 3+. Now what you really for, let me just go back here, in this case is to find the couple where the E0 cell value is actually between your peroxo disulfate and your iodide here, which is actually between your 0.77 and 2.01. So as long as the E0 value of this couple is between 0.77 and 2.01, you can actually do this reaction. So here you see likewise here the cobalt can do the same thing. I'm just going to show you the answer quickly. Or your manganate can also likewise do the same thing. With the, because the E0 cell value is in between your peroxo disulfate and your iodide E0 cell values here, iodine E0 cell values. So this is for cobalt, and this is for your manganate. So basically this sums up the transition metal. As I said, if you would like to try your hand at trying some of these questions, because actually they are related to the electrochem using E0 values, to see feasibility, please do so accordingly. I'll put up the answers here onto Blackboard here together with this video, so that you basically would have completed the syllabus for the prelim exams as well, so the A-levels. Alright, see you then.